Thank you very much. This is probably the biggest audience I ever had for a semigroup talk, so this is great. And if you think that the topic is a bit self-referential, then you are totally right. What I'm going to talk about semigroup modeling computations, and I'm going to study semigroups by using computers. So it's pretty much self-referential, but that's okay. So who am I? Yeah, exactly. I'm a software engineer. This guy is a mathematician, so I do research using computers, and I teach traditional mathematics classes, probably in a non-traditional way, because I don't see the difference between mathematics and computing, and that sort of comes through that. So this talk will give you a simple and easy understanding of semigroups, and I think many of you already have that. So this will be another example. So it's sort of just enriching the concept. And of course, it's connection to computing on a very low level. And one of the key ideas here is that you should get also a sense of what are the open problems we are working on. And also some ideas about the nature of mathematical research software. So first, what's a semigroup and how does it capture computation? So, well, you can get the abstract definition, you will not have problem with it. It's just a set with an associative binary operation, okay? So what does it mean to have a binary operation? Well, you have a bunch of things and you pick one and you pick another one and you compose them and you get a third one, okay? So this common metaphor is the Lego bricks. When you have two pieces put together, then you also get an element which is sort of a Lego unit. But beware of the shortcomings of the metaphor, because, well, you only build bigger things, while if you're in a semigroup, sometimes you put together things and it collapses down to nothing in a way. You might call this operation multiplication. That's a traditional way of doing it because, well, it's abstract algebra is just an abstraction from the behavior of numbers. But you might also call it just composition. And another familiar thing, associativity, and that just says that grouping is arbitrary. The way you do the composition doesn't matter as long as the sequence is respected. So then one might say in sort of in a philosophical way that, well, okay, this is just a model of time, okay? So there is one after the other. But this means for us that, well, X, Y, Z is well defined. I don't have to give more information how you do the composition. So here's an abstract example. Well, I just have a set that contains three things denoted by the symbols 1, A, and B. And here's your multiplication table, or you can call it composition table. So that means that, well, you know, you pick this thing 1 and you multiply by A, you get A. Well, you can read that off from the table. Or you take A and B, multiply them together, and you get B. Okay, so this is a small riddle. So what is this object? Well, we will meet this one later. So here's my story. As claiming that, well, semigroups are the ultimate descriptions of computation. You can start with the traditional models of computers, and you start with the Turing machine. Well, okay, let's just make the tape finite, because, well, we want to talk about sort of real-world computers. So you end up with a finite state automaton. So this is something you know very well. Well, regular expressions of your in UI design, while you use a finite state automata, or we heard yesterday that you can do property-based testing with using state machines. So that's the one. But again, traditionally, finite state automata are used for a special purpose in theoretical computer science for recognizing languages. That's the regular expression application. So you distinguish between initial and acceptor states. So let's just forget about that. Let's just purely consider it as a state transition system. So you have basically a transformation semigroup. So here's an example. It's very simple. We have only two states, 0 and 1, and we have one operation, a flip. That's just a modulo 2 counter. Well, we can count from 0 up to 1. then well, the counter goes back to 0. But you can see the relationship written down in equations that, well, okay, f squared, that means, well, okay, again, it's a metaphor coming from algebra. It's not really squaring, it's just f multiplied by f composed by f. That's E, and well, it's probably recognized this E. That's identity that does nothing. If you teach sort of abstract algebra to school kids, then they are totally fascinated with the idea of the doing nothing operation. And they are totally right, because that's group theory. So this multiplication table is quite special, as you can see. It's very small, but it's all the rows are just permutations, okay? And if you are interested in the thermodynamics of computation, well, then it's the permutation groups, which is sort of they are sort of very special transformation semigroups. Well, then it's of prime interest. Okay, let's have another example. Here's the flip-flop, and it's just 1-bit memory. So what you can do, well, you have the identity, which you can consider sort of as the read operation. Okay, you can read of what state we are in, and we have 2 resets, C0 and C1, and that just means that whatever state you are in, if you get C1, then you go to state 1. So that's the, you know, destructive memory update. So this is really 1-bit memory. And if you check, you know, we can talk about that. Well, these constant maps, as you can see, they're columns in the table. Well, it's really just the same element repeated. That says that it's a constant map, no matter what is on the left side. So I can write down it's sort of as a law how they behave. Okay, so yeah, the question is that is this composition table familiar? And the answer should be, oh yes, we've seen this before. That was the abstract multiplication table I showed you. And well, okay, they are the same. Well, to be more precise, they are isomorphic. If you use this mapping, then you can see that, well, it's basically the same structure, only the names differ. Well, I can tell you that in general, this is not as nice that you just put the 2 multiplication tables together and you just read of, these are the same, because they might be, you know, in different order. But more on that later. So here's another one, still with just 2 states, and that's the full transformation semigroup. And what I did now is, like, I'm not showing all the arrows, because, well, some of them can be guessed, because I have the flip operation, and if I do the flip twice, well, that's the identity, okay? So I also have that one. So this is quite typical in semigroup theory. That's the way you can grab the object, your semigroup, you give generators, okay? And then, so you don't give the full multiplication table, but you give a few, and well, you do all the products and see what you get exactly. So this is quite an important object, the full transformation semigroup, because this contains all possible transformations on 2 points, 2 states. So these are, if you have a computer which is restricted to have only 2 states, these are the computations you can do, okay? And so if you like it visually, so what you need to do, if you start with the automaton, how you turn it into a semigroup, well, in the automaton word, you think of like, oh, okay, just tracing a single state transition. It's like you are in that state and you go to another one if you receive an input. But for the semigroups, you have to change the perspective, and now you think about that, okay, each input symbol is a total function of the whole state set. So that's what you see down there, is that, well, the identity is just you have the 2 states and you don't change them, flip, well, you just flip these 2. And to further hammer this idea that you have the abstract description, which is just a full table of composition, or you can have some concrete representation. Okay, this is a particular example, a transformation semigroup. we can put these together into the same one. So this is the multiplication table. It's sort of abstract, but it also has the concrete representation. So how do you combine these? Let's have an example. Visually, this is just a diagram. So basically, I have 5 states here, and this is I just stack all the transformations and then trace the arrows. So one example is the red highlighted, and the resulting transformation will be that corresponding red arrow. Okay, so I'm basically, in a way, when I talk about the transformation, that's my semigroup element. I talk about what to do with all the states in one go. And well, okay, this talk is sort of code light, but this was quite a happy coincidence when I sort of, okay, let's implement this transformation composition in Clojure. And it turns out that, well, in Clojure, you have the vector, which is just an index sequence. And that thing behaves as a function as well. So I have these 2 inputs, 2 transformations, S and T, and I can just map the second one, because it behaves as a function, over the first one. And it's map V because I need to get a vector. So it's like, yeah, I'm as simple as that. It was just a happy coincidence when your operation in your domain is so easy to express in a particular language. Okay, so yeah, as you can see here, I have a bigger transformation. And so, okay, what does it mean that this captures computation? And it's like, well, yeah, I can turn every finite state automata corresponding transformation semigroup, or I can have the full structure. You give me how many states you have, and well, it describes all the computations. And well, yeah, this is sort of very low level. Okay, this is like the particle physics of computations, because so how many possible states we are talking about? So let's. So this is not a typical computer today. Well, this is where I started, and it's good enough to show. So just a rough calculation is like if you have 64K of RAM, and then it's like how many bits do you have? And it turns out that it's like slightly more than 500 million bits of memory. So that means that this machine can be in 2 to the power 500,000 different states, okay? So that's my n. So what's the size of the full transformation semigroups? How many transformations we have here? Well, it's just, if you have n states, n to the power n, it's an easy combinatoric. So we have 2 to the power 500,000 to the power 2 to the power 500,000. So I just want you to imagine this number for a moment and try to hold it in your hand. And yeah, of course you can't do, because this is just way over that. Okay, so that might be a different story when we talk about decompositions of semigroups, how we build up hierarchical structures. So of course this is, yeah, if you want to understand what a little cat is doing, is clearly you don't look at the quarks and the atoms, because that's not the right level of description. Okay, so I've been talking about single semigroup. Now let's have what sort of relationship we have between them. And this is the idea of the homomorphism. And in the special case, it's isomorphism. And this is the definition. So it's like, well, yeah, you have a map phi from the source semigroup to the target semigroup, that for all elements x and y in S, this is true. Okay? So this is how it's written in textbooks and in mathematical monographs. And it's not easy to understand if you just look at it. Well, at least I had problem with it. Then I realized that what happens here is that it's a type inference issue. So in mathematics, sort of the type inference is agreed to be there. So it's not written explicitly. But we can do that. I can say that, well, I can use different symbols to represent the operations in the 2 semigroups. And now, as the question is, in which semigroup is the composition done? And that you can see that once it's done in S, and the other side of the equation it's done in T. So that might explain. But if you prefer a more visual explanation, well, the blobs are sort of missing there, but as the source semigroup and as the target semigroup. And what happens here that if I, this is the very idea of the computer. I want to get from X by using the operation Y to X and Y, okay? But that's a long way to do, and I don't like to do that. For example, it's just arithmetic. I want to do some calculation, but my brain's capacity is not enough to do that. So that's why I map the inputs over to the computer and the state of the computer. And the computer can do the corresponding operation. And then, of course, I just get it back, get the number back to my domain. This is the idea of the homomorphism. So that means that if it's a systematic relationship for all X and Y, this is true. That means, well, it's emulation. It's for computer science people, it's easy to say that, well, homomorphism is just the idea of emulation. It's a bit more explicit. So again, a very simple example. Well, we have the modulo 2 counter, and we can embed it into, we can find an isomorphic copy inside the full transformation semigroup on 2 points, and that's our phi. Now just using numbers. So yes, of course, there is a lot more to the story because it's, in general, you don't have the isomorphism. You have sort of a relation. It's not just a bijection. It's a special relation. It's not a function. But roughly, this is the idea. So now, the landscape of open problems. So yeah, that's Akita. I'm not from Tokyo. It's really from countryside rice fields. So, okay, I have questions that are very familiar to you, but I'm sort of asking them on the very low level, on the particle physics level. So it's what is computable with limited resources? So yeah, it's a practical everyday question. So I can make it a bit more precise mathematically, and I can ask what is computable with n states, okay? And now we know the language that's the question that, well, okay, the full transformation semigroup, all transformations of n points, forming a semigroup on their transformation composition, they contain everything, okay? All the possible computations that you can do with n states. So I can just find all the subsemigroups. So this is the question of enumerating all the subsets of a semigroup. That is also a semigroup, okay? And so that's one thing we try to do, and you will see the results soon. So here's another question. How to measure computational power with precision? Well, sure, the crudest measure is that, well, is your device or is your language is Turing complete in a way or not, okay? So it's like, well, can it compute everything or not? But what we are trying to do here is a more fine-grade analysis of that. It's like if you give me a certain computation you want to do, the question is that, what is the minimal number of states you need in the computer to be able to do that? And that's the question of embedding into a suitable transformation semigroup, full transformation semigroup on n points. So finding the minimal n. And well, okay, here's another one, which is familiar to you. How can we establish the correctness of computations? Sure, using formal verification if it's possible, feasible, available. But otherwise, what do we do? Well, just beyond looking over the code several times. Well, we try to solve the same problem in a different way. And if we get the same result, then we are sort of getting convinced that this is the right result. So this is the sort of in computational experimental mathematics, this is the sort of de facto standard of verification. If like two different groups can calculate the same thing and the numbers agree, then, well, okay, that must be right. So the question is, using a set of generators, what are the different ways of expressing the same semigroup element? So it's like if a computation is defined by a sequence of those elements. So that's one particular solution to solve the computational problem of getting that particular element. So how many different ways are there? So this is counting paths in a graph. And the question is, what is different anyway? So computational results. Some of you might have seen these numbers and the Sydney closure meetup. That's like 2 years ago. That means that that's sort of the speed of progress we have in this. And we could go up to 4 states. So now we know all possible computations with 4 states, but that's where our knowledge stops. Okay, it's up to conjugacy. That means relabeling the states. So up to that symmetry, we have 132 millions of them. Okay, so that's the computational power of 4 states. And if we draw all these 132 millions of them and their sizes, so how many possible transformations they contain, then we have this graph, and we just have no idea why we have the 6 peaks and why they have this huge peak. So there is no mathematical explanation for that. And of course, we like nice diagrams, so we did another one. Now we are counting the idempotence. Idempotent is the thing which is safe to repeat. You might know this one again from programming. So E squared is just E. It's an operation that if you're not sure whether it's finished, you can do it again to make sure it's finished. And we have a very pronounced peak in around 60 transformation semigroups. No explanation. Okay, so talking about software tools. Yeah, it's good to know that you are how far you are from null and null. So in order to get those results, we use it's computer algebra system. It's called GAP, and it's a very nice system. So if you are interested in abstract algebra but in computational size, this is the system to go to. And we have several packages, several different purposes to do this, to get these results. But the thing is that, well, yeah, that's, when you do mathematics and you publish a paper and saying that, well, there are 132 million blah, blah, blah semigroups, and you get a bit paranoid, because what happens if this very special calculation hit upon some very weird bug somewhere down in the stack? And so I had to do recomputation, okay? So no one else will do that because it's a result already computed. So in academics, once it's published, it's like, well, yeah, done. So I have to do it myself, right? And at that particular time, I was playing with Clojure, so it's like, oh, yeah, let's re-implement the whole thing in Clojure and see what happens. And up to now, I got the same number, so we are getting more confident. And you know what happens when you do is like a toy implementation, and it's like, oh, you do it differently, you do it better, then you realize, oh, I can actually do something which I couldn't do in the original one. So now this is like a mainstream tool, it's not a shadow implementation. So now we have 2 things, and it's like, yeah, that's mathematical research for you. And well, you know, it's just to mention it and to show some code, the idea in our calculations, we just do graph search. That's what it's like. All the algorithms just graph searches. And I realized that, well, okay, I kept rewriting the same graph search in different contexts. So it's like, well, it's an obvious thing to do. Let's just abstract it away. And once you are in Clojure, then you can abstract it away. You can use the reducers, and you can use the parallel version of it, which is for our computations is actually not performing that well. So that's another research question, why we don't get that much of a parallel improvement. So the summary, that beyond the way you use semigroup as a useful abstraction in Haskell, for example, you can think of it as an abstract pattern of associative composition, or you can just simply think of it as a multiplication table, or just a bunch of equations describing how the elements compose, or you can think of them as mathematical descriptions of computing devices. And once you have that, well, so what is a computer? You can answer that by computerness spreads by morphisms, okay? So being a computer is being able to emulate other computers, okay? the question, okay, so then how do you start? That's rather more interesting, because if you heard about reversible computing and the idea that, well, basically we have the laws of physics are reversible, time reversible, and on top of that we have the full transformation semigroups, right? It's computers, and we know that there is no algebraic morphism from a group into a semigroup. So something funny is happening on there. So that's another interesting talk. And my point is that computation is far from being fully understood. I'm not interested in doing research per se. It's just the question. I would be just happy to read about results in science. But the questions I asked, there's just no one bothered to do it. So that's why I'm doing it. So, yeah, we are hiring. If you need a serious programming hobby and you like the topic, then come and talk to us. And otherwise, well, thank you very much for listening.